Hello everyone, I am Saurabh Kumar, an exploration geophysics student in IIT Kharagpur. Today we are going to discuss and/or graphs as a part of classical AI. Formally defining an and/or tree, it's a graphical representation in the form of search space where we reduce the problem into subproblems in order to solve the subproblems and hence arrive at the solution of our main problem. From the name itself, it suggested that and/or graph is composed of and/or nodes. An AND node represents a given decomposition which has to be selected, whereas an OR node represents a choice between possible decomposition. The number of decompositions can be anything. We will be using goal reduction method to solve the problem. This is an AND OR tree where our initial state is node A. This problem has to be decomposed into subproblems where we get B, C, D and E as the subproblems. B and C are connected using an AND operator, which is here signified using an arc between B and C nodes, and hence these nodes B and C are AND nodes. Whereas D and E are OR nodes. In order to solve A, either B and C can be solved, or D can be solved, or E can be solved. After selecting any of these subproblems, we decompose further until goal state is reached. If we reach a node which cannot be decomposed further and the node is not satisfying itself for goal state, then we consider such nodes as failure nodes. Otherwise, if we find the goal state, then the node is termed as success node. Now consider an example where a boy collects stamps. He wants to get rid of the initial number of sets that he carries, that is a winning match, bat and toy. Now his friends are keen collectors of different items, and this boy can exchange the initial items or the items he has at any given time with the following exchanges. The first one can be one winning match can be exchanged with a comic and a pencil, or this winning match can be exchanged using a bat and a stamp. One bat can be exchanged with two stamps, or one toy can be exchanged with two bats and a stamp. Now as we can see, we got 5 states here, and hence our objective is to carry out exchanges so that all the items are converted into a single state of stamps. The number of stamps can be anything in the set. So what we got is our initial state, which is composed of winning match, bat and toy. The transformation rules will be describing our search space and the decomposition into subproblems. These rules are being generated from the rules that we set up in the problem. If we have the node which is composed of M, that is winning match, then it has to be replaced with C and P, or it can be replaced with B and S. If we got B in the node, then it can be exchanged with 2S, that is 2 stamps. And if we got a node with T, then we can exchange it using 2 bats and 1 stamp. And hence our goal state will be a set of single state of stamps which can be of any number. In order to solve the problem using AND or tree, my friend Rohit Kumar will be covering up this topic. Thank you.
So, hello everyone, my name is Rohit Kumar and I am a final year student of the department Geology and Geophysics in Raw Limits Exploration Geophysics course. So, in our last part, we have seen the theoretical parts of AND and OR graph. So now we will see how AND OR graph graphically explained. So let's first differentiate between OR graph and AND graph. So here is an example which shows we have to buy TV sets, and there are three nodes for using which we can buy TV set. The first one is stealing TV, and second one is earning money and then buying TV. So now if we consider this first node, then we can say that TV set can be directly get from stealing TV. So this part is directly converting to end node, and for this if we want to buy TV, so first we have to earn money and then buy TV. So this is kind of cyclic. So this whole have to done together. So we can say that this is an and node. So this is represented, and node is represented as this symbol arc. So if we divide this graph, so we can say that this part is or, and this both including is and part. So in our last part, we have seen we have taken one example and written a pseudocode. So let's solve that question graphically. So the question was: consider a boy who collects stamps, which is denoted as S. So he has for the purpose of the exchange a winning match M, a bat, a toy. In this case, he has some friends who are keen to exchange bat, match and toy with some comic pencil and stamps for the stamps. So condition is we can exchange a match for comic and pencil. We can exchange match for bat and stamp also, and for bat we can exchange stamp and stamp, and for toy we can exchange bat and stamp. So let's see how we can solve this question using and or graph.
Start.
So let's take initial nodes as MBT, match, bat and toy. So we can exchange M with CP, which we can write as. We can also replace match with CPBT, BSBT, and we can also replace M with two stamps. And we can replace B with T with two bat and one stamp. So there is nothing given for C and B, so we can exchange B and T. So let's start with B. B can be replaced with two stamps or two stamps, and now we can exchange T, and for T it was given two bat and one stamp. Now we can replace one B. Again, one bat can be exchanged with two stamps. So now we can't exceed further because we don't have any condition for C and P, and our goal is to get stamps. So our goal is to get this all S. But here we can't replace CP, so this is failure node. We can say this is failure node. So now considering BSBT, we can exchange B with 2 stamp. So then we can again exchange B. Now we can exchange T with 2 bat and 1 stamp. And now again 2B with stamps. So we can say this node is successful because we are getting all the stamps in our final node. So this is now taking MSST. So we can exchange M with CP and BS. So there are 2 nodes, CP and BS. So now we can see this node can be ignored because this is same as this. So we know this node this CPSST will get us to a failure node. So we can ignore this and proceed with this. So we can replace B with 2 stamps. And again we can see that this node is also same as this. Okay, so we can follow this path and get us to success node. Here we can replace M with CP and BS again. CP. We can ignore this node because this is also coming in this node. Replacing all this B, we can get here 1 B. B will be replaced with 2 SS and we will get this. So this can be ignored and we continue with this BS BBS. So we can replace 1 B. So it is and again and we can see that this SSS BBS is coming here. So again we can follow this node and we will get this success node. So this is how and an OR graph is solved.
Hello, my name is Chirag Singhal. Today I'm going to discuss one of the algorithms for AND OR search, that is the AO star algorithm. So the basic idea behind this algorithm is that it involves two major operations. First, the top-down operation, graph drawing, which involves the picking out of the best available partial solution subgraph from the explicit graph given. Then a leaf node of this subgraph is expanded. Then the second operation, which is the bottom up, involves the revising of costs at nodes of this subgraph and marking them as solvable or non-solvable. Now, for the problem we are given G, which is the implicitly specified AND OR graph, N, the starting node of the graph, T, the set of terminal nodes, Hn, the R heuristic function which calculates the cost of solving sub problem at the node N. Our objective is to find a minimum cost solution tree. This algorithm requires two arrays and one heuristic function. One of the array is the open array, which contains the nodes that has been traversed but yet not been marked solvable or unsolvable. The closed array, which contain the nodes that have already been processed, and our heuristic function hn, which is the distance from the current node to the goal node. The steps in the AO star algorithm are the step 1. The algorithm first places the starting node into the array open. Then it finds the most promising solution tree, say T0. Then it selects a node n that is both in the array open and a member of the subtree T0. It then removes it from the array open and places it in the close array. Then in step 4, it checks that if the node n is the terminal goal node, then it marks it as solved and mark all of its ancestors as solved. But if the starting node is marked as solved, then we have found our solution and the algorithm exits. In step 5, if n is not a solvable node, then the algorithm marks n as unsolvable, and if the starting node is marked as unsolvable itself, then our algorithm returns failure and exits. Then in step 6, the node n is expanded and all of its successors and their hn value are found by the algorithm, and then the successors are pushed into the array open. Now in step 7, all the successors of the node n go through these uh, same steps from step 2 to step 6 until we find a node which is our terminal goal node. Then in step 8, the program exits when we have reached our terminal goal node. Now, my friend Bhutwala Raj will explain this algorithm with an example. Thank you.
We will now continue with an example for AO star algorithm. So here is the initial state of an AND OR graph problem, and the initial values of the graph can be seen as in the figure. So the problem can be defined as the given GST variables, which each of them mean G is the implicitly specified AND OR graph. S is the start node of the AND OR graph, which in the figure is node A. And T is the terminal node, which in the figure is node F. And the values of the intermediary nodes are governed by the heuristic function values, which help us estimate the cost of solving the subproblem at n. Now, the aim of this example is, or the problem is, to find a minimum cost solution tree. In the next step, I will explain how we can arrive at the solution. So, starting from the source node, we evaluate the first level node and then move on to the nodes with the lesser cost. Now, in the square brackets, I have denoted the cost of a particular path. So, starting with the source node, that is node A, there are three edges that we can see, that one is an AND node and another is an OR. So which can be seen by a hyper wedge in between. So at first we can start calculating from the left side. So for the end node, we have our total cost as 1 plus 2, which are the cost of the node B and C, and to reach those nodes the cost is 4 and 5. So total cost is 12, and to reach the node D we have total cost of 8 plus 5 is equal to 13. Now since 12 is less than 13, we move forward with the left side. Now we try to traverse deeper on another level of the graph, which will give us the next connection edge between B and C. Now we will update the values of the newly discovered connections by after going deeper, and the value of node B has now been updated to 2 plus 2 is equal to 4, and that way the whole path has a cost of 4 plus 4 plus 5 plus 2 is equal to 15. So this is more than the cost on the right side. So now we shift to the right side and dive into the deeper nodes of the right side until we reach the terminal node. So first we take the path A, D, E and evaluate the new values. So because of that the cost of E is 1 and the edge has a cost of, to reach that edge is 2. So the value of node D will be 3 and hence the total cost will be 5 plus 3 is equal to 8. Now we will also try to reach through another node and also through the an existing node edge between E and F. And now we will evaluate both these paths ADEF and ADF, and the one with the least cost will be our solution. Now trying with the ADF path. The value of node F is 0, hence the cost to reach the node F from D is only 4, and hence the updated value will be 9. And since the cost of the edge between the E and F is 3, which will make our total cost 10, we eliminate that and we now settle with the path ADF. And hence A, D and F, all our nodes are solved. The minimum cost path is node A to node B to node F, and the total cost is 5 plus 4 is 9. Thank you.